for this example, the site was at 2041 UTC on 9 July 2026, and we measured 42 degrees 40.4 minutes on the sextant height. So with our slide rule, the first thing that we're going to do is apply several corrections to get our observed height. So first we set the inner index to point to the minutes of our observed height, so 40.3. And then using the cursor, we will select the -1 minute of sextant index error that this particular sextant has. Next, we'll correct for the sun's semidiameter by rotating to July on the little calendar. And because we had a lower limb site, we will go clockwise, which will add to the height. So we bring that to the inner index. Next, we select on the inside our height above sea level, or height of eye, which is 4.5 meters above sea level. And then to correct for refraction, we're at 20 degrees C. So we'll select where that lines up with the 40 degree above the horizon, and we see that our corrected minutes are 50.3. So our height observed is 42 degrees, 50.3 minutes. And because we're going to be computing our latitude from this, we actually need the zenith angle, which is 90 minus that. And so we can directly read the minutes of that as from the red values here. So this is going to be the complement, so 9.7 minutes. And 90 minus 42 would be 48, except we're a little past 48 because we have this fraction. So we're at 47 degrees, 9.7 minutes. And because we were facing north, we're going to define that as a negative zenith angle. To compute the declination of the sun at the time of our observation, we need to go to our almanac for July 26th, where on 9th of July at noon, it would be at positive 22 degrees, 19.1 minutes, so that's in the northern hemisphere, and it's heading south at 0.3 minutes per hour. So to compute the declination at the time of observation, we set the minutes, 19.1, and in black because it's in the northern hemisphere. And then we will use the red times, since it's headed south. So for 2040, there's 20. So we'll follow that back to where that intersects the 3 line for the 0.3. And we get it. The corrected declination should be 22 degrees, 16.3 minutes. To compute our latitude, it's going to be the sum of our declination and our zenith angle. And our declination is still currently set on the with the cursor, 16.3. So if we set the inner index there, we can then rotate the cursor counterclockwise to the red 9.7 since we're subtracting it, and we see that it should be 6.8 minutes. However, note that the zenith angle is bigger than the declination, so we're going to end up changing signs there. So in that case, we'll want to use the 53.2 minutes. And then 22 plus minus 47 is minus 25, but since we've got this fraction left over, it's going to be minus 24 degrees, 53.2 minutes for our latitude. To plot our latitude, we will measure approximately 53 degrees on our plotter paper, and we're minus 53 degrees, remember, so somewhere around there. So our line of position, we can plot, we know that we are somewhere around here at, so this is minus 24, this is minus 25, so this is minus 24 degrees, 53.2 minutes. To compute our approximate longitude, we can again use the slide rule, and we can see that at 2000 UTC, the sun would have a global hour angle of around 120 degrees. And then we can also use that to measure, we were at 2041, or 41 past the hour. And according to our almanac, the equation of time for that today is minus 5 minutes 15 seconds. So if we put the inner index on the 41, and then we sweep back 5¼ hours, we can see that we will need to add 8. We'll need to add about 8 point something. So we can just call that 9 degrees that we need to add. So 120 plus 9. This should be about 129 west, approximately. We will refine that later with our afternoon sight. For our afternoon sight at 2230 UTC, we measured a sextant height of 35 degrees, 58.4 minutes. So to correct that, we're going to do the exact same process. I'm just going to quickly breeze through that. 58.4 with our 1 minute, minus 1 minute of index error. Our July calendar, lower limb, and note that we cross the outer index, so we're going to have to remember to carry the 1 when we get to the end of this. Then again, correcting for 4.5 meters above sea level, and then 20 degrees C with at 35 above the horizon gives us almost exactly 8 minutes. And remember, we have to carry the 1, so our height observed for this afternoon sight is 36 degrees, 8.0 minutes. To plot the intercept, we'll need to calculate our local hour angle between us and the sun at the time of our observation, 2230. So the global hour of the sun at 2230, at 2200 it would be 150 degrees, and if we point the inner index at 30, and then we move backwards by the equation of time for the day, 5 minutes 15 seconds, we can see that the time past, or the distance past the hour is going to be 6.2. So our global hour angle then is 156.2 degrees. And from our noon sight, we know that our approximate longitude is 129 west. So we're going to subtract the amount west from that, and we should get 0.2. 27.2 degrees for our local hour angle. We'll also need to compute the declination at the time of this afternoon observation. So again, going back to the almanac, it's positive 22 degrees, 19.1 minutes, and changing at 0.30 minutes per, negative 0.30 minutes per hour. So again, we can set our inner index on the 19.1, and since it's a negative, we're going to use the red value, so this red 2200. And again, they don't change a huge amount as we get up there, so basically where it intersects, so it looks like about 15.5 degrees for our declination at time of our afternoon observation. And then we will also need to compute the approximate zenith angle for our assumed position at minus 24. So we're going to subtract minus 24 degrees from that, which gives us 46 degrees 15.5 minutes for our approximate zenith, which we'll need for our computing HC. To compute HC for our afternoon sight, we could consult Pub 249 and look up the contrary name and interpolate, or we can compute it more exactly with another slide rule. So for this one, what we'll do is we'll start on the logarithmic side of the slide rule, and we'll select the declination on the red arc, the red outside arc, so we'll set 22 and 15 minutes. We'll then rotate the inner wheel to line up with our LHA of 27 degrees 12 minutes. We then, and we need to be sure that we note that that is on ring number 4. We then move the cursor to our approximate latitude of 24 degrees on the black of these, and we can measure a transfer angle of 24, 55, 57. So 25 degrees 57 minutes for the transfer. So we flip over to the linear side of the slide rule, and we can, because the transfer angle is low enough, we can actually select it here, 25, 55, 57 on this outer ring, and then we set the inner ring to the zenith angle we've computed, 46.15. So we have to find 46. Black on the spiral. So there's 40, 46, and we said 15, so there's 10, there's 15. And we note that's on ring 1. We now take the cursor and swing it all the way to clockwise to this outer index. We note that we've crossed the inner index, so we end up here, and so we need to go from ring 1 to ring 2, and we can read our computed height from red, so it's going to be 36 degrees, there's 36, 30, 40, looks like 36, 43. So HC for our sight is 36 degrees 43 minutes, and that is in the same ballpark as our height observed, so that seems like a good fit. The next step in plotting our intercept is to compute the bearing to the sun, and we do need to do a little pre-computation again. We need to again add our longitude, so we've got minus 24 minus 24. So that gives us 60 degrees 43 minutes for HC minus latitude. So for this we will start again on the linear side, and we will align the two indices. Then we're going to move the cursor to that value we've just computed, 60, 43, so there's 30, 40, 43. We're then going to bring, and we have to note that that is ring 2. We're now going to bring that inner ring to our declination, 22 degrees 15 minutes in red, so that a little further. So there's 22, 10, 15. And now we're going to rotate this counterclockwise to the index, and we note that we cross that. So we're now over here. And And we started ring 3, we then have to move out 2 for the other one, and we've crossed, so we have to read from the very outer ring, 3 minus 2 minus 1, and we get 27, 10. So we can write down that value, 27 degrees, 10. Flip over to the log side again. We're going to set, again, black for 24 for our approximate latitude. We're going to select the that transfer angle that we just got, the 27, 10, 27, 10, and then we're going to go noting that we're on ring 4 there for 2710. No, that is not. So the last thing we need to do before we plot our intercept is we have to compute the HC minus our observed height. So that's 36 degrees, 43 minutes, minus 36 degrees, 8 minutes. And we can do that on the slide rule. We can also just do that in our heads, but so if we set the, there it is, the inner index to 0.243, we can then move the cursor to minus 8 on the red, and we read 35 minutes. And there's a positive 35 minutes. We can also make a little note here. HC greater than HO means that we are away from the assumed point. So that is away. So we will now draw the bearing. Zn is 328. So 328. And we're going to be away, so we'll need some on the back side. So the sun is that way at 328 degrees. And then we'll need 35 degrees. Yeah, 35 degrees of latitude. How far away we are. That should put us about here. And then, so our line of position is going to be perpendicular to that, and where it intercepts our noon sight latitude, we're assuming we've been at anchor or something this whole day, is going to be our position. Now we're at around 25 south, so we can use the mid-latitudes here to measure 20 or 21. So this is going to give us our longitude of 129 degrees, 21 minutes west, and our latitude from this morning of 24 degrees, 53 minutes south. And so that is how we compute our latitude and longitude from our noon sight and an afternoon sight using the intercept method. An important question, however, is can we trust our chronometer during these measurements? So one way to do that is to use an observation of the moon if it's up at the same time as the sun. So if at 1745 on that same day we were able to measure the height of the moon, the height of the sun, and the distance between them, we can use that to compute the current time. So first we'll need to apply the usual corrections for refraction and height of eye. However, we need to compute the corrections with dip and index error, and then again with refraction and parallax added in. So let's do the sun first, since we're familiar with that. we'll set 37.6 on the slide rule, point the compass at it, and add in our index error. Usually subtract our 1 minute of index error. We'll come to the sun's semidiameter for July, and then we will swing around for the 4.5 meters height of I. And then we're going to stop before we add in the refraction, and we're going to put a corrected value of 25 degrees, 48.8 minutes. And then as we add in the refraction, 25 degrees above the horizon at 20, we get 25 degrees, 46.5 minutes. Now, to do the same thing for the moon, we actually have to compute some additional values. The first is the moon's semidiameter. So we flip the slide rule over to the moon side, we set the cursor on the index, and align our approximate latitude, say 25-ish degrees on this SD augmentation curve. And from the almanac, we can see that the horizontal parallax for the moon right now is 59.4 as of July 9th, around 1800. So we follow this curve to 59.4, where that crosses the lunar semidiameter, and we can see that its semidiameter is 16.3 minutes. And then the other value we need to compute is the parallax. So we realign those indices. And for 38 degrees, at so here's the 59.4. There's the 30 degrees, so this is, so that would be 35, 36, 37, 38. So it looks like it is 46.8 minutes of parallax for the moon. And the little diagram here reminds us that the parallax makes the moon higher. So we flip back over, and again, we'll set 1.8 on our minutes, do our index error, and now rather than using the calendar, we have to subtract the semidiameter because we did a upper limb measurement. So we'll align the inner index there, and then we will swing this backwards to 16.3, and then to correct for 4.5 meters. So that gives us, and note that we've crossed the index as we did this, so we have to carry or subtract 1. So we are 40.7 minutes and 37 degrees. And now we have to add in the refraction and the parallax. So we'll select 38 degrees at 20, and then we'll bring the index back around, and then we'll go positive to 46.8. Notice we cross the index. 46.8. So that gives us 26.4. And again, we've crossed the index, so we're back at 38 degrees. So these are now our updated, corrected observed heights for the sun and the moon, both with and without refraction and parallax. We also need to correct the lunar distance, since it was measured between the two, the sun and the moon. So again, we can do that by selecting 47.9 on our on the slide rule, and then we can add the suns the same way we did before by selecting July, swinging to the index, noticing we cross the outer index, and then adding the 16.3 for the moon, so 16.3, and that gives us then a lunar distance of 65 degrees, 20.0 minutes. Two additional computations that we need to do is the difference between the moon and the sun measurements. And again, the slide rule can help us with the minute calculation. So if we set 40.7 for the moon, and then we're going to subtract out 48.8, which comes all the way around. We note that we're going to have to carry, so we'll just say 48.8. So that gives us 52.1, and then 37 minus 25, and minus 1 from the carry. It's going to be 11 degrees, 52.1, and then again 26.4, and then we're going to subtract out 46.5, so again counterclockwise, crossing the index, 46.5 gives us 39.9, and then 38 minus 25 minus 1 again, 12 degrees, 39.7. Okay, now that we have all of the pre-computation done, we need to adjust the lunar distance for the refraction and parallax. So to do that, we're again going to return to the Haversine wheel. So step one is we're going to rotate the outer cursor to the difference between the moon and the sun without correction, so 1152. 1152, and then we're going to rotate the wheel to the observed lunar distance, 65 and 20. What do we say? 65, 20. So there's 65, 10, 15, 20, and then we're going to rotate the cursor counterclockwise to the index, noticing that we've crossed in, so we need to move one ring in, and we can see that the transfer angle that we're going to need is 63 degrees 57 minutes. So flipping over to the log side, first we're going to select the height of the moon without refraction, so 3740 on the black, so 3730, 40 there, and then we're going to rotate the inner to give us that transfer angle, 6357 or so, and then we can adjust for the sun, though in this case it's not going to matter, so we're going to bring this all the way to the sun height of 2548 on the red, 2548, and we can see the transfer angle is 77, excuse me, the angle between the two azimuths is about 77 point something, but since there's only 2-minute difference in the height of the sun at this scale, we're not really going to see anything. So instead, we're now going to go back to the height of the moon on the black, 38 degrees 26.4. 38 degrees, there's 30, there's 26. And this gives us a return angle of 63.35. Going back to the linear side, we are going to select the difference between the refracted and parallaxed sun and moon on the black. So that's going to be 1239, so 1240-ish or so. And then we're going to select that transfer angle that we just had, 63.35, so 63, there's 30, 35. That's on ring 2. And then we are going to go clockwise to the index, noting that we cross the carry. So we go from ring 2 to ring 3, and this gives us a corrected lunar distance of 65 degrees and 8 or 9 minutes. Let's call it 8 minutes. So we are finally ready to try to compute our time. So if we go to our almanac, we can see that the at 1700 the moon would be 65.35. At 1800 it would be 65.0.4. So our corrected 65 degrees 8 minutes lies somewhere in between there. So in order to do that interpolation, we can use the moon side of the wheel. So and because it is changing negatively, we're going to use the red numbers. So we start by pointing the inner index at that 33.5 on the red, 33.5 on the red. And then if we go to the 0.04, again on the red, we can see that that's changing around 33 minutes per hour. And our we are at 8 minutes, so we can bring this to the 8. And so where that 33 line intersects, we follow it out, and we can see that it is about 45 and a half past the hour. So based on the moon, 1745, 30-ish is an approximate. And considering that our chronometer said it was 1745 when we took the measurement, I think our chronometer is pretty accurate. And that is how we can validate it using the clock that is the moon. I realize that there is a whole lot of stuff going on with these two slide rules, and that they may seem complex and challenging to use, but with practice they get pretty fast. In fact, I'm significantly faster doing my sextant corrections with the slide rule, and I'm getting to the point where I can do my HC and bearing calculations faster on the haversine wheel than I could looking them up in the Pub 249. And since you can read out the bearing or the bearing minus 360, it saves me quite a bit of math. Also, I don't have to do the interpolation. So overall, I really prefer to do this versus carrying around the books. And the lunar is a real challenge to get good sights, but it's quite fun to be able to tell time without a chronometer. If you check out the website, I've got instructions for how to use them, and you can download, print your own copies, and hopefully they will be fun for you as well. Thanks for watching.